He's Executive Vice President Technology of ASML, and I'm so happy that you're with us to talk about your technology, but also your vision about the global ecosystem for science and technology. Thank you so much.
Thank you very much.
Thank you so much.
Ladies and gentlemen, it's my great pleasure to be here in this wonderful location for this wonderful week. First of all, I'd like to thank Dassault Systèmes for inviting me. Merci mille fois. Today, I'd like to share that AI, that was all my French, sorry. Today, I'd like to share that AI is enabled by advanced chips, as mentioned already by Patrick. Chips made by an industry marching to the beat of Moore's law, an empirical law of economics, a law enabled by optical lithography. And a leading company in this field, ASML, was named a relative obscure Dutch company by the BBC only 5 years ago. A company that brought an artificial sun into the fab of our customers. And we are thus able to print features 10,000 times smaller than the diameter of a human hair. If you're interested to learn what made us a leading litho company, please stay tuned, as I plan to share a critical ingredient. And I will finish my presentation by giving some examples how AI helps us and our customers to make better products for a better world in the future. So as we know, society is going from chips everywhere to AI everywhere. It hits multiple sectors like agricultural innovation and also the robots, as was already mentioned before. And a plurality of different applications is expected to add another roughly $10 trillion to the GDP in 5 years from now. So it's a field that brings a lot of value, economical value. It's not only the size of this field, it's also the speed at which innovation takes place. I find this myself a very intriguing graph. It took Facebook 4 years to get 100 million users. It took DeepSeek 7 days. So here is a clear example of an ever-increased pace of innovation of our industry and how AI penetrates the world. So let's have a look at one of these AI data centers and what is in the heart of it. So if we zoom into this data center, we will see racks and racks of NVIDIA blades. If we would take one out and then zoom into one of these chips, what you will see that these chips are made on 300 millimeter silicon wafers. And we produce about 100, we image about 100 fields on a single chip in 20 seconds. Such a single wafer will contain 15 million transistors when produced in the most advanced 3 nanometer node. Looking what's inside such a transistor, we will see that it is actually a three-dimensional structure. At the lowest level, the finer structures is where we store our data or do our processing. But we have to get the data in and out, we have to get power in and out, so there's a three-dimensional structure of multiple layers. The finest layers at the bottom, more coarser structures on top. And if we look what we are able to print today, the finest structures is about 8 nanometer lines and an 8 nanometer space. And as I already mentioned, to put it in perspective, 5,000 lines and spaces pairs would fit in the diameter of a single human hair. So to print such a very small structure is done, or to print any structure, is done by the litho system, which is basically a nano copying machine. There is a pattern stored on the mask, which is illuminated by light, and that pattern is repeatedly imaged onto a 300 millimeter wafer, and thus the pattern is transferred into a single layer, and layer after layer are being built. As mentioned in the introduction, what is critical, what is basically describing the pace of our industry, semiconductor industry, has been defined by Gordon Moore in his visionary paper in 1965, where Gordon Moore noted that an ever-growing component count, the number of components per chips would increase. Originally, he said doubling every year. And as such, he predicted that would be something like a mobile home computing, which remember, 1965, the audacity to write that down. My colleague Sander had the pleasure to interview Gordon Moore. So he flew to Hawaii in 1914 to interview the man himself, and I'd like to share a part of that interview with you.
So I took this doubling every year and extrapolated it 10 years from 1965 to 1975, from 60 components to 60,000 components on a chip. A pretty wild extrapolation. And it turned out to be ridiculously accurate. One of my colleagues called this Moore's Law. Rather than just being something that chronicles the progress of the industry, it kind of became something that drove the progress of the industry.
And indeed, it did so for many decades. So one of the questions is, then how are we able to print smaller and smaller lines into a single chip? And the answer is in this formula, commonly referred to as the Rayleigh criterion, although I must admit, historical facts are it should have been called the Abbe criterion. But I'm not sure there's any Germans in the room, but they should make that change. But it's very simple. The critical dimension are the smallest features you can print, scale linear with the wavelengths of the light, denoted by the lambda. It is proportional to 1 over the numerical aperture, which is basically if you sit at the wafer and you look up to the first lens element, the opening angle, the sign of the opening angle is called the numerical aperture. And there's a factor in front of it which has a physical limit of 0.25. So a quarter wavelength over NA is the smallest feature you can print with optical lithography. And over the years, the industry has progressed from one wavelength to the other, changed the color of the light roughly every decade. We went from a mercury lamp, G-line, to an I-line lamp, mercury, 365 nanometer, krypton fluoride laser, 248, argon fluoride laser. And within this decade, we actually increased the numerical aperture by making bigger and more powerful lenses. And as you can see, we went from about 0.5 using the G-line lens about 40 years ago to the immersion lens, which has an NA of 1.35. And then we made a giant leap. The industry made a giant leap. The industry moved from 193 to EUV, which has a wavelength of 13.5 nanometer. Roughly a 15x reduction in wavelengths. Remember, the critical dimension scales with the wavelengths. So this gave unprecedented shrink capability. But the EV wavelength change did not come overnight, nor was it easy. First pioneering work in Japan, the US, and Europe. In the mid-80s of the previous century, I myself started the program at ASML in '97. It took until 2019 to have your first phone with a chip made with EUV. And what made it so hard? If you look at the light, EUV light can be seen in nature, but only in the corona of the sun. This gives you EUV. So that means we had to make it artificially. We had to make it sun into the fab. And the way we did it is by shooting, after some trial and error, AI was not at our rescue at the time, we ended up with this setup where we shoot a very powerful laser at a tiny tin droplet. You shoot a tin droplet about 30 micrometer into a vacuum vessel. You hit it with a laser twice, first to turn it into a pancake, then to generate a plasma, making of about 500,000 degrees Celsius. And you do this 60,000 times per second. And that way you can generate enough EUV light to have a production-worthy high-volume system. The light is then next captured by the optics and shined towards the mask, which is finally then imaged onto your wafer. So why was it so hard? Next to the science of understanding plasma and physics, there were major technical innovations required on the engineering side. To put it in perspective, we shine with a 30 kilowatt laser on one of these tin droplets. This is the equivalent power of a military system that is used to shoot down tanks, satellites, etc. So you don't want to be a tin droplet in your life ever. Secondly, the optics. This is even more astonishing. The optics comes from a good partner called Zeiss. And the aspheric optics is made with a precision of 20 picometers, which is about 1,000 times more accurate than the James Webb Space Telescope. And not only are they able to produce it so accurately, they also position the mirror with unprecedented accuracy. they can shine, it's equivalent to hitting with a beam of light from the Earth a coin at the moon. So this was just one of the technological challenges that had to be mastered next to the source. And to make it cost effectively, you have to produce many of these wafers per hour, up to 200 wafers, each 100 fields per hour. Meaning you have to you need to have very fast moving stage technology. Stages today accelerate up to 30 G, which is about 4 times faster, higher acceleration than a modern fighting jet. So let's switch gears a little bit. So what's the company that did it all? Well, first let's look at the beginnings, the humble beginnings of ASML as a spin out of Philips. We zoom into Eindhoven, which is in the south of the Netherlands. You see the Google Map Earth of today. And then within a second, the picture will appear of ASML. ASML is the wooden shed in front of the Philips building. It started with 31 employees as a joint venture of Philips and ASM. And to be very honest, Philips wanted to get rid of it. So they separated them. Today, now we are a worldwide operating company with sites in the US, in Asia, as well in the Netherlands. But this is our headquarters where most of the R&D takes place, where we build, I dare to say, the most complex machines mankind has ever built. And we are the second biggest tech company, and we went from 31 to 44,000 employees in just over 40 years. So how did we do this? This is now a critical slide to explain our secret. So out of necessity, when we were spun out of Philips and we were only 31 people, the industry at the time used to be very vertically integrated. So Philips or Nikon, one of our current competitors, they have their own glass to make their own lenses, to make their own steppers, and then with a more vertical integrated system to make your own chips for your own TVs. We work through a very tight network of many partners. We call it an ecosystem. The ecosystem contains of customers. Customers are not only important because they pay the bill, customers are also critical to determine your long-term roadmap. Our lead time to design and realize a new system can be 10 years. So it's critically important to align with your customers what, after 10 years from now, would bring value to them. Secondly, co-solution partners. You need a mask that holds the pattern. You need a resist with which the light interacts. So these are, for instance, JSR and Hoya. But also those that do the etching and deposition in the factory. TEL, Lam, Applied. Technology partners that turn science into innovation. You see them also mentioned worldwide. Academics. It's not a classical model where you do a PhD study and then years, and that still happens a lot, but and rightly so. But we actually often stumbled across something that worked and didn't understand it. So we had to work with leading experts, leading academics in the world to help us to understand and make the next step. Last but not least, suppliers. I often say it's relatively easy to do an invention. I did a few myself. It's extremely hard to do an invention that can actually be built. So we have a very tight network with academics. So this collaborative ecosystem is a key factor in our success. And a very close interaction and the fact that you trust each other, it's a very old-fashioned word, I know, is also very critical in the key of our success. And I'm very pleased to also share our latest addition in this network, Mistral. Mistral is probably well aware, a French company which will help us to accelerate and make better use of AI, even more so than we have done so in the past. That brings me to the last section of my presentation. How do we use AI? And we use it across the value chain. We use it in design, we use it in production and customer support, also at a customer base to set up and utilize our tools. And in few of times, I like to give 4 examples along this value chain, but there are many, many more examples that could be given. First, let us go back to the EUV source, which I already introduced. We shoot with a very powerful laser at a stream of tin droplets. But next to EUV, the big question is, where does the tin go? If the tin ends up at our optics, we will quickly lose the light. So the system has an elaborate system of hydrogen flow, which actually picks up the tin, forms also tin hydrides, and it has to be pumped away from the vessel to avoid it completely clogs. And what is an important element is the tin scrubber that has to remove the tin from the vacuum to avoid everything is clogged downstream. So the function of the scrubber is simple: remove the tin, but it's a complicated engineering task to be done. So we did it in a classical way. You know, you have all your modeling, which is actually very elaborate, because you need plasma modeling, you need flow modeling, you need thermal modeling. But we have, after many years, we came up with a baseline design scrubber. Then we trained the model based upon our physical model and used it to generate many, many more designs. About 12,000 designs were generated in a relatively short time. And at first glance, these AI-generated designs look very favorable. So I'll give you a few KPIs. The pressure drop, so that means you want to have a low pressure in the vacuum, not to absorb the light. And you don't want to have big pumps, so a significant improvement. The thing was much smaller. But then when we had humans look into it, and again, let me emphasize the importance of collaboration between science and suppliers, we quickly found out the thing could not be made. It was way too complex. So we had to retrain the model and ended up with a new design that actually does improve pressure drop, volume, the tin survival rate, so it captures more tin, and it was in fact easier to manufacture. So the key point of this example is AI was great, but it had to be trained with physical modules, and the human in the loop was still very important. The second example I'd like to share is optical proximity correction. Let me explain it in a few sentences. As mentioned, we have a pattern on the mask which we want to print repeatedly on a silicon wafer. But due to the fact we are very close to the diffraction limit of the light, what you see in the mask is not what you get on the wafer. So you tune your mask to get a feature on the wafer that is as close as possible to where you want it to be. So by taking parts of the mask away and adding other parts in the mask, you see this in this animation, you end up something on the wafer which you are looking for. This is called optical proximity correction. Extensive physical models exist to do the job. However, they are typically iterative. And if you talk to customers, they say, well, the results actually vary by the human in the loop. It takes a long time to train the engineer. The manual work is painful. And the biggest challenge today is the number of iterations or the time it takes. Using machine learning, it brought many advantages. One of them, and here I again use a customer quote, one of our leading customers, it greatly accelerated the learning of new engineers. Next to this, there are a number of publications made on this. When using the inference, it was also much faster and more accurate. So this was a great example how AI is used in a product at our customer side. Back to the source, again an example of optimizing the source. So the first example was on designing the source, or an element of the source. This was on optimizing it. There are many sensors looking into the plasma, side sensors looking into the light, measuring the flow, etc. We used the data from all of these sensors and fed it into a physical informed neural network by using historical data as well as physical constraints. And using this physical informed neural network, we optimized the set point and fed that back into our source, into the many actuators. Actuators, you can think of how to shape the light source that hits a droplet in time, in spatial domain, etc. And by doing so, we were able to achieve 1% more light. Well, that may sound like very little, but 1% more light corresponds to about 0.5% more productivity. And 0.5% more productivity of a tool that costs several hundred million euros is still very significant value. Last but not least, holistic lithography. Again, let me introduce it with a few sentences of what we mean with holistic lithography. Traditionally, ASML sold what we call a scanner, this nano copying machine. And we complemented that by what we call compute, or nowadays you would call it the digital system, and metrology. Metrology that can measure anything, any function within the scanner, but also metrology that can measure what actually was produced, the image produced on the scanner, and measure it outside the scanner. And there's an endless stream of data coming from one of these systems, including the metrology. All of this is fed into a digital twin scan, digital twin, and used to optimize the settings of the machine. And why is this so critical? Why is it almost becoming impossible to do it in the classical physical modeling way? It has to do with A, the requirements we need to do, but B, also the knobs we have available. One of the challenges is not only to produce smaller features, but as you can imagine, there's a three-dimensional structure, as I showed at the beginning, and you have to add the next structure on top of the previous structure. This is what we call overlay, typically within a fraction of the width of a line. The overlay went down, scaled down proportionally. So the overlay had to improve 3 orders of magnitude over the last 20 or 40 years. And we could do so by using the many knobs we have in our system. The knobs include how we position the stage, the reticle, the lenses, and the actuators in the lens, as well as the light going at your reticle. So we have at our disposal about 100,000 knobs that is fed by 1 million data points. And using all of this in combination with a digital system, we were able, here now you see the measurement, the measured results, we were able to improve overlay by 3 orders of magnitude. A very critical usage of the data that becomes so abundant that it is almost impossible to do it, to absorb it and make best use of it in a classical way. With that, I have come to the end of my presentation. I hope I shared with you how semiconductors fuel the AI boost we all live in, how ASML with its systems helps the Moore's law that builds these very powerful semiconductors, and then going full circle, how the AI uses us to build better systems to all of our benefit. With that, I thank you very much for your attention.
Thank you very much, Jos. This is very, very impressive, I must say. We have time for some questions. I'll start with one. We've seen how you, of course, contribute to the AI, let's say, explosion with those unique chips. We've seen how you use AI for your own development and different processes. And talking about Mistral, is there also a feedback loop in terms of the design of the chips themselves for pure AI activities like inference? Or are you staying, quote unquote, agnostic with respect to the usage of the software stack on top of ASML chip?
That's a question that deserves a week of
we have the week.
Talks.
We have the week.
But short answer is the well-known von Neumann bottleneck, you know, where we used to separate processing from storage, and nowadays we pump the data up and down, and it takes 90% of the energy. And the biggest challenge, in my view, of AI, the biggest bottleneck is probably the energy consumption it takes.
Yep.
So the industry is bringing the storage and the processing closer together by bonding chips on top of each other, which again has unique requirements to the tooling that is used. And on top of this, so this is just a hardware problem solving the von Neumann bottleneck, and each software needs to be tuned. This hardware-software co-optimization. But again, this is almost a bootstrap problem or a bootstrap thing we are encountering. AI is helping also with those designs, and the designs are needed to bring AI forward. So yes, there will be a revolutionary change in the way we architecture or compute power.
Okay, thank you very much. We have 30 seconds for a last question,
30
very short
seconds.
one. And if not, because everybody wants
I'll
to break.
be around all day
Exactly.
today and tomorrow.
So let's thank again Jos Benschop
you very much
for this amazing presentation.